All right, today we have some acid-base reactions, which is topic 4.8 for AP Chemistry. So, acid and bases can be defined in several different ways. So there's a definition made by Lewis, so we call that the Lewis definition, but the way that we are going to use is the Bronsted-Lowry definition. And there's like this little weird little O. Little O, some German O. So an acid is a substance that donates hydrogen ions in aqueous solution, and a base is a substance that accepts the hydrogen ions in aqueous solutions. So we'll see that in the next example, but water acts as a base here because it accepts a hydrogen ion, and HNO3 or nitric acid acts as an acid by donating a hydrogen ion. So here we can see that this goes here and accepts this hydrogen ion because this is a hydronium ion. That's how you spell it, hydronium ion, which is H3O positive, and sometimes when we have an H3O positive, we just denote it H positive, which just is essentially a proton added to this water. And then we have the acid, which is in turn turned into the conjugate base because it donated this hydrogen. We can see that this hydrogen lost it, so this is our acid because it donated the hydrogen, so it donated this H positive, and so acid and our conjugate base goes together. So that's how we know that this conjugate base is our NO3 negative or a nitrate ion. We can track that backwards too and saying, okay, well, our conjugate base backwards is going to have a hydrogen or a proton attached to it because it's going to donate one when we go forward to the forward reaction. So in our reverse reaction, it's going to accept the proton, which is our HNO3. Since this is a strong acid, we're not going to have a reverse reaction. We're just going to have a forward because it's going to ionize completely. But you can see that our water acts as a base because it accepts this hydrogen right here. And water is a species that is amphoteric species, which just means it can act as an acid or a base. So it can act as both an acid / base. So, so in this one, water is actually our acid because it's giving up the hydrogen ion and turning into our hydroxide ion right here. If we write water instead as HOH, kind of its Lewis dot formula or Lewis structure formula, you can see that these waters are bonded together like this, and that's how we write HOH, and we can see that this H here, let me choose different colors, sorry, so we can see that clearly. This H is donated to the ammonium ion, so NH3, ammonia, is our base, and we can see that it accepts, so we have 3 hydrogens attached to the nitrogen group, and then here we get this NH4, so it accepted the hydrogen, and this would be our conjugate acid, and this would be our conjugate base. Remember, the acid and conjugate base goes together, and our and our base and conjugate acid go together. So that's how we can see, and this is a reversible arrow, so that means it's going to go back and forth because this is a weak base and a weak acid. Water isn't a strong acid or a base. And so when we have weak bases and weak acids, that means they don't fully protonate or deprotonate if we're talking about an acid, so they don't fully ionize. And so ammonia acts as a base, by accepting a hydrogen ion. Yeah, so conjugate acid-base pairs are related by the donation or accepting of hydrogen ions. So again, this is the same problem that we just saw. So we're just accepting and donating. It's all about hydrogen movement or proton movement. So a strong acid base undergoes complete ionization, like we just talked about. So there's not going to be a reversible arrow. HCl would be the strong acid in this case. So pause the video real quick and try to find out the conjugate acid base pair here. So we have our strong acid here, HCl. So that means when we donate this hydrogen over on this side, this will be our conjugate base, which matches up with our initial acid. And this would be our conjugate acid, because when we go backwards, if we look at the backwards reaction, say this has a backwards reaction, even though it technically doesn't, we see that we're giving up this H positive. We're giving it back up if we go backwards and turning back into water, which has one less hydrogen ion. And then this base plus the water here, so this water is going to act as our acid, because if we look on this side to the hydroxide ion, this is our conjugate base. And one quick note, that the conjugate acid base of a strong acid or base are weak. Sorry, this is bad handwriting, but they are weak. So, which just means that they don't fully ionize in solution. So, yeah, they have very little ionization. The equilibrium will often go to the reactant side, which means we'll have more unionized species. So we'll have, in this case, we use HA to say weak acid, and then HB would be our weak base. When we get to acid bases, we'll look more at this, but our weak acid here, we're going to have much more weak acid in solution on the reactant side than we are our A negative, which is our conjugate base, because it's not going to fully ionize, which means all the hydrogens are not going to come off. And that makes sense, right? We'll have more hydrogens attached to the original acid, our weak acid, than we will to our conjugate base if it's not going to fully ionize. So neutralization in this topic, this unit, chemical reaction, we're just going to look at neutralization reactions mostly. So one of the most important reactions of acid and base is their ability to neutralize one another. So that's when a strong acid and a strong base react, and that is when the hydrogen ions in the acidic solution react with the hydroxide ions in the basic solution to form water, and the other product is a salt. So that will be an ionic compound, is what a salt is. So if we have a strong acid and base like hydrochloric acid and sodium hydroxide, we get the salt, which is sodium chloride, table salt, and our water. Our ionic equation, we split up all of our ions, so we have H positive plus chloride plus sodium plus hydroxide yields this sodium and chloride broken apart, and then the H2O. But our net ionic equation for a strong acid-base reaction is always, oops, the heck, yeah, sorry. Accidentally pressed the home screen button. This will always be H positive plus OH negative for a strong acid-base reaction. And just make sure we put state symbols here. Quickly, let's look at an example. So let's write a whole formula, ionic and net ionic equation for the neutralization reaction between aqueous solutions of potassium hydroxide and sulfuric acid. So we have KOH, which is our, usually if we have a OH, our hydroxide, this is a base. This is a strong hydroxide because our group 1 metal hydroxide and group 2 metal hydroxides are strong. And we have H2SO4. Aqueous, remember, acids are always aqueous even if it doesn't tell us. And so what does that yield? Well, this is sometimes referred to as a metathesis reaction, but essentially just a double replacement. We're going to switch partners. So our K is going to switch with our sulfate, which has a charge of -2, so we need 2 potassiums. We have aqueous, and this will be plus our H2O, because we have the water as one of our products, and so we need 2 Ks on this side, and we have 4 hydrogens on the reactant side, only 2 on the product side, so we need 2 here, and that is our molecular equation. And then we need to write we'll just write the net ionic. So remember, strong acid, strong base is going to be our H positive plus our OH negative yields our H2O. But from our coefficients, we have 2K, we can also show it this way with our 2, 2, and 2, but since they're all equal, they're all 2s. We don't have to show those, but we can. It's not incorrect to say this. And then, of course, if we write our whole ionic equation out, we'll just see that the potassium is going to cancel out and the sulfate's going to cancel out because we have an equal ratio on both sides, and they're not involved in the net ionic. So that is a little introduction to acid-base reactions. Let me know if you have any questions or need more practice.